Hey everyone, and welcome back to the channel. Today, we're diving deep into one of the most fundamental concepts in neural networks, activation functions. If you've ever wondered how these intelligent systems learn to make complex decisions, this video is for you. They are, quite literally, the heart that brings a neural network to life. So, what exactly are activation functions? Think of them as gatekeepers within each neuron of a neural network. After a neuron processes its input, a simple weighted sum, the activation function decides whether that neuron should fire or be activated, and if so, how strongly. But their most crucial role is introducing non-linearity into the network. Without them, no matter how many layers you add, your neural network would only be able to learn linear relationships, essentially just a fancy linear regression model. This non-linearity is what allows neural networks to understand and model incredibly complex real-world data, like images, speech, and intricate patterns. Let's start with one of the older, but still relevant players, the sigmoid function, represented by sigma of x equals 1 divided by 1 plus e to the minus x. It's an S-shaped curve that squashes any input value into a range between 0 and 1. This makes it incredibly useful for tasks where you need a probability as an output, like in binary classification problems. Think, is this email spam? Or does this patient have the disease? Its smooth gradient is a pro, but it suffers from a major drawback, the vanishing gradient problem. For very large positive or negative inputs, the gradient becomes extremely small, making it hard for the network to learn effectively in deeper layers. Next up is the Tanh function, or hyperbolic tangent. You'll notice it looks quite similar to sigmoid, but its output range is between -1 and 1. This zero-centered output is a significant advantage over sigmoid, as it often helps with faster convergence during training. Its formula is tan x equals e to the power of x minus e to the minus x, divided by e to the power of x plus e to the minus x. While Tanh addresses the zero-centered issue of sigmoid, it still faces the same vanishing gradient problem for extreme input values, limiting its effectiveness in very deep networks. Now let's talk about the king of activation functions for hidden layers, ReLU, or rectified linear unit. Its formula is incredibly simple. ReLU of x equals max of 0, x. If the input is positive, it outputs the input as is. Otherwise, it outputs 0. ReLU's popularity exploded because it largely solves the vanishing gradient problem for positive inputs, and it's computationally very efficient. This simplicity makes training deep networks much faster. However, it does have a dying ReLU problem, where neurons can become inactive if their input is always negative, leading to zero gradient flow. To address the dying ReLU problem, we have Leaky ReLU. Instead of outputting a strict 0 for negative inputs, it allows a small non-zero gradient, typically 0.01x. So the formula is f of x equals max of alpha x, x, where alpha is a small constant like 0.01. This ensures that even for negative inputs, there's still a tiny bit of gradient flow, keeping neurons alive and preventing them from dying during training. It maintains the computational efficiency of ReLU while mitigating its main drawback, often leading to better performance in some scenarios. Finally, let's look at Softmax, a crucial function primarily used in the output layer for multi-class classification. Unlike the others, Softmax takes a vector of raw scores, often called logits, and converts them into a probability distribution. The key here is that all the output probabilities will sum up to 1. This means it explicitly assigns a probability to each class, indicating how likely it is that the input belongs to that specific category. Its formula is sigma of z equals summation of j equals 1 to k of e to the zj divided by e to the zi. See on the graph how the bars represent the probabilities for each class, and if one input score is much higher, its probability dominates, while still ensuring the sum is 1. This is perfect when you need to classify an item into one and only one category, like identifying an image as a cat, dog, or bird, but not all three at once. To summarize, here's a quick comparison of these activation functions. Sigmoid and Tanh are good for older networks or specific output needs, but they struggle with vanishing gradients and are computationally slower. Sigmoid for binary output, Tanh if you need a zero-centered hidden layer. ReLU and Leaky ReLU are the workhorses for hidden layers due to their speed and ability to combat vanishing gradients, with Leaky ReLU solving ReLU's dying problem. Softmax is exclusively for multi-class output layers, turning raw scores into a probability distribution that sums up to 1. So what are the main takeaways? ReLU and its variants like Leaky ReLU are generally your first choice for hidden layers in deep neural networks due to their efficiency and gradient properties. They're fast and they work well. Always choose your output layer activation function based on the nature of your problem. Sigmoid for binary classification or multi-label, and Softmax for multi-class mutually exclusive classification. Finally, and this is crucial, experimentation is key. The best activation function can sometimes depend on your specific dataset and network architecture. Don't be afraid to try different ones and see what works best for your model. I hope this deep dive into activation functions has been helpful. If you learned something new, please hit that like button, subscribe for more AI and machine learning content, and let me know in the comments which activation function is your favorite to use. Thanks for watching, and I'll see you in the next video.